So I'll go ahead and share my screen. There we go. We're good?
Yeah, I can see it.
All right. So I'm going to talk about multiple scales in time. And I'll start with ordinary differential equations. And then I'll do a specific example of what's called a resonant triad, which is relevant to a lot of things, but specifically an application called wave turbulence. And then I'll go into and talk a bit about what's called wave turbulence theory, which is for PDEs. And so the details are a little bit different there. And I'd like to just point out that a lot of the material here, material on wave turbulence goes back 50 years, but there's been a nice paper that I particularly like by Colm-Connaughton and co-authors in Physics Reports 2015. So if you do want to follow up on wave turbulence, I feel like that's a good place to start. All right, so we're going to start with a forced linear oscillator. F is my forcing, and we can solve this, Calc 1, ordinary, diff EQ. We can solve this pretty easily with an integrating factor, variation of constants, and here's your formula for the solution. And then we're specifically going to be interested in the case where you're forcing using just a pure oscillation, a pure Fourier mode at a frequency omega hat, which is not necessarily the same as the frequency of the oscillator. Okay, and then to do that, you just plug in e to the I omega hat t here, do the integral, and you get this. And the integral you can get in closed form, and I'm just calling it delta because I'm going to need this expression later. So x is something that's going to show up throughout my slides. It's the difference in the frequency of the forcing minus the frequency of the oscillator. So I can think of this delta as being a function of two arguments, time, and then the difference in frequencies. This delta function is it has singular behavior though. So if you pick any x, any difference in the frequencies, and then let time go to infinity, this delta is going to remain bounded, except if you force with a frequency that's equal to the natural frequency of the oscillator, in which case you get that this thing grows linearly in time. So the delta function is a singular function. When you force an oscillator at its natural frequency, it grows linearly in time. That's a phenomenon called resonance. And I've just got the absolute value of this delta down here is, I've just written the formula. All right, so that's one oscillator forced at a resonant frequency. Now we're going to go to a system, a nonlinear system of three ordinary differential equations. This is just coupled oscillators. So Z1, Z2, Z3 are all oscillators with different frequencies, omega 1, 2, 3. And they're nonlinearly coupled, but the coupling is weak. I've got an epsilon here that's less than 1. The C's are called, what are they called? Coupling coefficients or interaction coefficients. And you can show, and I think Zach is going to use this for a homework problem, that you can show that if the sum of the interaction coefficients is 0, then this system conserves the energy, where energy is just the sum of the squares of the amplitudes of the modes. Okay, I'm not going to prove it though. All right, so we can do asymptotics on this, right? Asymptotics class. So we can take our modes and expand in an asymptotic series. I'm using superscripts for asymptotic order because I've already used subscripts for something else. And I'm only going to go out to first order here. So if I plug this in and then collect everything at order 1, leading order, I just drop out the nonlinear terms, and I'm just left with unforced oscillators for all of the modes, and you can just write the solution down. Okay, so it's e to the I omega t times the initial condition. Pretty standard stuff there. Now we go to order epsilon and pick up the corrections, the z superscript 1. Okay, so You go back to the equation, you collect all the terms at order epsilon, and this is what you get. So Z1 is going to be basically a linear oscillator, linear harmonic oscillator, that's forced by the leading order solution, the Z0 solution. And we know what the Z0 solution is, so we can plug it in. And if you plug it in and do a little algebra here, this is what you get. Okay, so these things are all constants, the C1 times Z2, Z3, whatever. Everything in the square brackets is just a constant related to the initial conditions. And then the forcing here is a function of time. It's just a pure oscillation as a function of time. So this is just each one of these Z1s is just a forced harmonic oscillator, and we know the solution to that. We just write it down here. Now I've left off the initial condition piece. I'm assuming that the initial condition for your solution is taken up at leading order, which means that the next order corrections have just initial condition 0. So the solution here only comes from the forcing, and there's your expression for it. I've written it in terms of the delta. All right. When the forcing is resonant, right? So we have a solution, we have a formula here. It's only really interesting though when the forcing is resonant. And that happens when the sum of these three frequencies is exactly 0. So if you go back to the way back here, I have my delta function x. When x is 0, then I'm forcing at the resonant frequency. And back in this expression for this one, the first argument of the delta is whenever that is 0, you're forcing at the resonant frequency. And that happens when the sum of the three frequencies for each oscillator adds up to 0. If you have a different formula for the nonlinearity, then you'll get a different condition for resonance. But for this particular nonlinear system that I've set up, that's the condition for resonance. Now, if one of the modes is resonant, then they're all resonant. So if Z1 is forced resonantly, then it implies that Z2 and Z3 are also forced resonantly. So the whole triad is resonant, and that's why we call it a resonant triad. Now what happens here is the Z1, if it's a resonant triad, the Z1 corrections grow linearly in time. That's what we saw, they grow as T. So if you let T go out to epsilon inverse, then you have your total solution, your total asymptotic solution here is going to be epsilon times something that goes like T, and T is 1 over epsilon. So that cancels out, and your asymptotic series breaks down. It becomes disordered. So Z0 is no longer bigger than Z1 if you wait that long in time. So you can keep doing this and going to higher and higher orders if you want to. But if you do, your solution is only going to be valid for times less than order epsilon inverse. If you want to go to longer time scales, we need to do something different. Just heuristically, I've written this long wordy slide here. So maybe I'll just tell you instead of having everyone read the slide. Heuristically, energy is conserved, right? But the condition of the sum of the three interaction coefficients being 0 implies that energy is conserved. But the interactions are weak. And so the interactions are exchanging energy between the different modes. And you can see this in the sort of single time scale asymptotics that we just did. So Z1 is going to be forced by Z0 and Z2, or Z2 and Z3. And it's going to grow linearly in time. So energy should be sort of coming out of the two modes that are forcing Z1 and causing that Z1 to grow. But in this single timescale asymptotics, that doesn't happen. You see one of the things grow, but the other two don't decay. So the single timescale asymptotics is kind of violating energy conservation. And it's happening on a slow timescale. So what we're going to do next can be thought of heuristically as sort of trying to restore energy conservation by going to something with multiple timescales. So down here at the bottom of this wordy slide, what we're going to do is we're going to introduce a new time variable. So the original system only has one time variable, t. We're going to introduce a new independent variable. It's not really independent because tau is just epsilon t, but we'll introduce it and we'll pretend basically that it is an independent variable. So we'll write z of t is now z of t and tau, two independent variables. The chain rule, so we can expand derivatives with respect to time as a partial with respect to the first time variable times dt dt, which is just 1, plus a partial with respect to the second time variable and times d tau dt, and d tau dt is just epsilon. So that's how we're going to expand time derivatives here. Once we do that, we just go back to a normal asymptotic series and plug everything in and expand. Once again, at leading order, the order 1 part of the equations is just a system of linear unforced oscillators. But now these are partial derivatives. Technically, this is a system of PDEs, even though tau doesn't appear anywhere. All right, so we can actually solve it exactly the same way that we would solve it before, but in a sense, we're using separation of variables to solve this system of PDEs where the independent coordinate tau doesn't show up. But anyway, we get our leading order solution here. A of tau is going to be the amplitude of this leading order solution. So we see just by looking at our solution that in principle, the amplitude of the leading order solution can change, but it can only change on the slow time scale. And that was something that was absent from the previous asymptotics that we did. But on the fast time scale, it just behaves as the regular old oscillator. And the initial condition is basically giving you what the amplitude is at the initial time. Now we are not done with the leading order solution. This leading order solution is not closed because we don't know what the A's are. If you write this down and box it and say, that's my answer, you're not done because you don't know what A is and you don't know how A evolves. So we have to keep going. We actually go to order epsilon in the equations. And if you just plug everything in, this is what you get at order epsilon in all the equations. I think I just, oh boy, where am I? Sorry, I'm lost. Let me find myself. Okay. Must have hit the wrong arrow button. All right. Here we go. We plugged it in. That's what I wanted to see next. All right. So this is just rearranging things from the previous slide. And you can see with respect to the fast time variable, the regular time variable t, the next order corrections, the superscript 1, they're just linear oscillators that are forced by something that's a constant on the fast time scale t times a pure oscillation frequency. And I've assumed that this oscillator is resonant. Okay, so I've used that fact. Now what we know is we can write down the solution for this, for the corrections, for the Z1s. And what we'll get is something that grows linearly in the t time because of this something times the forcing at the resonant frequency. And we don't like that solution. We don't like that the corrections grow linearly in time. So we say, you know what, if we just impose that everything in the square brackets is 0, then we get rid of that problematic solution that grows linearly in time. Furthermore, that gives us a system of ordinary differential equations for the amplitudes A, and it's a system of ordinary differential equations on the slow time scale. Now, let's see. This is the system that you get. Doing where you set the square brackets to 0, that's sometimes called applying a solvability condition. And that can be a little bit misleading sometimes, because obviously the equation on the previous slide, that has a solution. It's just not a solution that we like, right? So if you want to think of this as a solvability condition, you can think of it as saying, you know what, I want to find a solution of these equations, but I want to find a solution that lives in a function space that I like a bounded, something that's bounded for all time. And the only way to get a solution in that function space is if you set the things in square brackets to 0. So solvability doesn't mean if we don't do this, there's no solution. It just means if we don't do this, then the solutions that you get are not things that we like. All right. So that's multiple time scales, pretty straightforward asymptotics. We're next going to get into wave turbulence, which is going to be lots and lots of systems of interacting waves, not just 3. And furthermore, in these very high dimensional systems, lots of interacting waves, the wave turbulence theory is interested in the expected value, sort of the mean value of the solution. And the way you can get that is by making the initial conditions random variables. So not like an ergodic mean, but you have random variables for the initial conditions, and then you want to average over the initial conditions to get the expected value. And you're not looking for the expected value of the solution per se. They're actually looking for the expected value of the energy in each mode, not the total energy, because that should just be conserved. But they want to know how much energy is in each mode and how does that evolve over time. We have it here from single scales. I mean, this set of ODEs will basically tell you the slow time scale evolution of the energy. You just square the A coefficients. When you have lots of interacting waves, though, you can't necessarily do this same straightforward theory. You need to do something else. I mean, you could try to do this, but it doesn't work out nicely. And so wave turbulence theory does something else because you have to do something else in order to make progress. So for some preliminaries, let's go back to just the single time scale asymptotic solution here. So I've got my leading order term. It's just the initial condition times a pure oscillation. And then here I've written down the order epsilon, the correction. This is for an arbitrary triad, not necessarily a resonant one, just arbitrary. And here's the delta. If it is resonant, then that's going to grow linearly in time. Otherwise, it stays bounded. And then there's some order epsilon squared correction terms. Okay. Now let's say the initial conditions, which you can see here, Zi of 0, Zj of 0, those are the initial conditions. Those are drawn from they're random variables, and they're all independent of each other. And they all have mean 0. Just for the sake of simplicity, they have mean 0, but they're definitely all independent, and they have a variance. Usually people will also say that they're Gaussian, but I don't need that necessarily for this. Now let's look at the expected value of the energy in one mode. So we're going to take Z sub I, square it. That's like the energy. If you want, you can add a factor of 2, and then take the expected value. So now I'm going to just square this expression up at the top, and I'll have the leading order term squared. That's here. And then I'll have 2 pieces from the leading order term times the epsilon term. That's here. And then everything else is going to be higher order. Now, when you take the expected value, this is just whatever energy you put in at the initial condition. And here you have an expected value at the order epsilon term. You have an expected value of a product of 3 initial conditions. But these initial conditions, we assume that they're all 0. Or sorry, they're all independent and they all have mean 0. So the expected value of this product is 0. So you don't see the breakdown here when you're looking at the energy. You don't see the breakdown in the asymptotic solution in quite the same way that you see it when you're looking at this at the actual solution. So the expected value of the energy versus the actual solution, we can see already that it's going to be a little bit different. All right. So what you can do I think I'm going to skip through some of the next slides. We actually want to look at the order epsilon squared terms. The epsilon squared terms are where the breakdown is going to happen. And the epsilon squared terms in the energy come from the epsilon term in the solution multiplied by itself and the epsilon squared terms in the solution multiplied by the leading order part. So in order to get these epsilon squared terms in the energy, you actually have to find the epsilon squared part of the solution. And it's straightforward, it's not hard to do. And I do it on the next few slides, but I am just going to skip through that because we don't really need it. Okay. So then when you look at the epsilon squared term in the energy, you've got the epsilon term in the solution squared. And we know for a resonant triad, that's a problem. The epsilon solution is going to grow like t. So when you square it, it grows like t squared. And that piece is going to look like epsilon squared times t squared. So it's going to blow up on the time, or it's going to become disordered on the time scale that you expect. T goes like 1 over epsilon. When you look at the second order term times the leading order term in the solution to give you the second order term in the energy, that is here. I've written this expression down. The E term we don't need. When you take the expected value, it doesn't go to 0. So these are all the initial condition terms in here are squared. So when you take the expected value of them, you just get the variance in the initial condition. And then the E term comes from like finding the solution of a linear oscillator that's forced by a delta term. Okay. And that actually, the E term here is going to go like t squared. So this is also going to be a problem on the time scale of 1 over epsilon. T goes like 1 over epsilon. So that's just a little preliminary stuff before we get into the PDE version. Let's see how I'm doing on time here. So here's just a simple scalar PDE. So use my solution. It's in one space dimension. I've got a weak nonlinear term here, so I've got epsilon in front of that. Some linear term here. And the linear term is going to have purely imaginary eigenvalues. I'm going to assume that we're on the real line, and that so L is going to be like skew symmetric. Its eigenfunctions are Fourier modes, and its eigenvalues are purely imaginary. So minus I omega k, those are the eigenvalues of the L operator. So when you take the Fourier transform, you get to here. The linear part is easy under my assumptions on L. And the nonlinear part, though, requires a little extra work. So we need to Fourier transform the nonlinear term there. And so we'll do that next. So I'm going to expand my solution in Fourier transform. And I'm ignoring all of the, I'm just using the simplest proportionality constant for the Fourier transform here. Right? I could define it to be unitary or something, but I'm using the simple version of the Fourier transform. Here's my expansion of d by dx Fourier transform. So now for the Fourier transform of the nonlinear term, I'm going to plug in these expressions and then use the definition of the Fourier transform. And I think I have one too many integral signs here. Yeah. I should only have 3 integral signs because I have 3 d differentials here. Interchanging the orders of differentiation and ignoring any problems associated with that, you get to this expression. This is not what people really use for the interaction, though. People use something else. So in order to get to the slightly nicer formula for the interaction, I have to do some changes of variables. So I'm going to assume that my solution, my PDE is real. U is a real valued function. It's not complex. So that gives me a nice condition on the Fourier transform, the Fourier coefficients. If I plug that in here and then I make a change of variable, all the 2 independent variables for the wave numbers, I turn them into minuses of each other. Then you get down to this expression here. And I still have one too many integral signs. So this is the expression that you'll usually see. And there's a few things I want to point out about this. Let me see what's on my next slide. Yeah. So first thing is that I've got this integral of a pure Fourier mode against dx. That's going to be 0 unless it's the 0 mode. Right? If the wave number is 0 and you integrate that over r, you get infinity. If the wave number is not 0 and you integrate that over r, you get 0. So this piece here, we can replace by a Dirac delta distribution. If you want, you can do a more careful limit argument and just say that we can take a weak limit of this thing and call it a Dirac delta distribution. And that tells us that nonlinear interactions between waves in this PDE occur in triads. So I've got 3 interacting modes. If I go back to my Fourier transform, I'm saying, all right, mode K, it interacts with other modes through here. Right, so I'll have like one mode that I plug in for u, a different mode that I plug in for d by dx of u. And the question is, which ones interact with mode K? You know, in principle, you could say, well, I've got lots and lots of waves. They could all interact, all to all. That's fine. That's a fine model of wave interaction. That's not what this PDE does, though. For this PDE, the only waves that interact are the ones whose wave numbers satisfy the condition k plus l plus m equals 0. Otherwise, they don't interact. So that's the condition for triad interactions. And then the coefficient of the interaction is basically this Im. For this particular kind of nonlinearity that I've set up, the interaction coefficient is going to be Im. So that's a triad, or you know, which modes interact, which sets of 3 modes interact. You can then say, well, out of all these modes that interact, which ones are going to be resonant interactions? And that's just the standard, that's just the standard condition there. Okay, I've rewritten it here. So here's my PDE. I switched notation to bring us back to something that's familiar for the triads. So for the triad model, I was using Z for each mode. And then for the PDE, I was using U. So now to get back to my Z notation, I'm going to take U and I'm just going to replace it by Z. So here I've got time evolution of the Fourier coefficient for mode K. It's got a pure oscillation, and then it's got the nonlinear interaction. It only interacts with modes L and M that satisfy k plus L plus M is 0. I've got my interaction coefficient, just like for the triad model. For this particular PDE, the interaction coefficient is Im. And then the actual form of the interaction is Z star, Z star, just like my nonlinear triad model. And that's why I actually did this manipulation on the formula for the Fourier transform. All right, if we go all the way back to my triad PDE, oops, yeah, here it is. So the nonlinear term looks like an interaction coefficient times epsilon times complex conjugate times complex conjugate. Now in the PDE, I have the same thing, but I'm adding up all possible triad interactions. So I don't just have 3 modes, I have an infinite number of modes, all interacting, well, all interacting modulo this delta. And to get the total effect on a single mode K, you have to add up all of the triads that it interacts with. All right, still good. So now to do wave turbulence on this, you want the initial condition for every mode to be 0 mean independent random variables. And you want to look at an evolution equation for the energy in a particular mode. And in the preliminaries that we did before, we know that in order to get that, we're going to need to actually go to second order in the solution. So not just order epsilon, but epsilon squared. Okay, and that's straightforward. This is your solution. Okay, it's exactly the same asymptotics to do it the one way or the other. You can base the fact that you've got an integral in here doesn't change anything. So leading order solution is pure oscillation. And then the next order solution, the corrections are just oscillations forced by resonant modes or forced by whatever the other two nonlinear actions are. So you have this delta in here. And then you could go to the second order and get those corrections if you want to. It's just a bit of a mess. To get the energy, oh, here we go. To get the energy, at leading order, you have this piece. At order epsilon, you have this piece times the epsilon correction. Just like in the preliminaries, the expected value of the order epsilon piece is 0. So now you have to go to get the epsilon squared pieces in the energy and see what breaks down, and then try to fix that using multiple scale asymptotics. And there is a difference here. So when you do the PDE, it's a bit different from the ODE. So there's two terms that contribute. You have the epsilon term in the solution squared, and then the epsilon squared terms times the 0 terms. I'm looking here just at the epsilon term squared. So here's my epsilon term times its own complex conjugate. And then I'm going to take the expected value. And the initial conditions are all independent. So if I have like ZL times ZL prime, if L and L prime are different, then the expected value of that is going to be 0 because they're independent. So the only terms that are going to contribute to this are the ones where L and L prime are the same and M prime are the same. So I'll move to that case. That's now the expression here. This is the order epsilon term in the solution squared. When I take the expected value, these two pieces respect to the initial conditions, they don't go away because it just becomes the variance. And now I have this absolute value of delta t squared. And we know what that formula is. Actually, I put it on like the second slide or something. It's like sine of xt over 2, right? But the absolute value is t squared, as expected for a resonant mode. But now that is sitting inside an integral. And this is the difference. With an ODE, you've only got one triad forcing itself. Here, you've got an infinite number of triads all interacting with one mode, and you're integrating over all of their effects. But the set of resonant interactions, the set of triads that interact resonantly and have this t squared term, it has Lebesgue measure 0. So you might expect, they don't do anything. Resonances don't do anything. That's not quite true. What actually happens is just that the effect of the resonances is not as strong in the PDE as it is in the ODE. So you have to do now some asymptotics on this integral. I don't know if you've done asymptotics on integrals yet, but basically you take this integral, you do contour integration, you deform the contour in the complex plane, and then you do the asymptotics, and you find that this delta squared, you can write it, and it converges weakly, not to t squared, which is what you would expect from the ODEs. It actually converges weakly to t times delta x. So the Lebesgue measure 0 set of resonances, that goes like t squared. But in order to get something that's not 0, you have to fatten that out, and you have to take things that are not just on the resonance, but that are sort of near the resonance. And when you do that, it attenuates the amplitude from t squared down to t. Okay. So that means actually that what happens is the breakdown of the asymptotics doesn't occur at time t goes like epsilon inverse. It actually breaks down at t goes like epsilon squared for the PDE. And there's a whole lot more asymptotics and a whole lot more complicated stuff that people do for these systems. And I'm not going to go over it. And we're almost out of time. But the idea is you write down equations for the time evolution of the energy in each mode. You asymptotically expand. You try to find the terms that are causing blow up, and you eliminate those terms using multiple time scales. So it's broadly similar to what we did with the ODEs. What you get out, that equation for the time evolution of the energy, is called a kinetic equation. And then usually people just look for steady state solutions. And those steady state solutions are usually in the form of power laws. So you find some expression, you start plugging in power laws and seeing if you can get a steady solution. So that's wave turbulence theory in a nutshell. I'm done. I've got 5 minutes for questions. Or 5 minutes, or, oh, I'm 15 minutes.
Yeah, no, that was nice, Ian. You have plenty of time for questions. I don't think anybody will complain if we end early. So
Okay.
yeah. Yeah, questions for Ian. So I had one, just kind of going back to so you have random initial conditions.
That's
I think I kind of missed it. So is that just like spatially independent? Is that a spatially independent noise process, or so I guess in the Fourier domain, you're expecting that you're going to have multiple terms of the same frequency from your independent initial condition. I guess how are you, like, if you're running this as a simulation or whatever, how would you generate that initial condition?
Yeah, so there's some interesting stuff with respect to simulation. With simulation, you can't do an infinite domain, of course, so you have to do a finite domain, which then means that you don't actually have an infinite set of waves here. In the integral, it means you have a finite set, and so actually things get a little different. So, but you have to assume that you have, if you just assume you have a very big domain, right, then some of the predictions of turbulence theory should still apply. For the initial condition, usually these things, you do it in a periodic domain. So you're actually operating at the level of the Fourier coefficients, and you just initialize those as all independent draws from random Gaussian. And then the amplitude of the Gaussians, you'll vary to set the spectrum of the energy spectrum. So you might have more energy at large scales, less energy at small scales, or whatever it is. Maybe you want to see how energy moves from small scales to large scales. So you can initialize it kind of however you want. I'll also point out, actually, though, that you do this whole machinery to work through to get the kinetic equations on slow time scales, and then you're looking for steady state solutions. And actually, the steady state solutions don't care about they don't know about the initial condition. So these questions about how do you initialize, when wave turbulence theory works, the questions about the initial conditions don't matter so much. It is
as long as your initial conditions involve somehow terms that will create this resonance condition. Could you conceivably cook up an initial condition that wouldn't lead to that?
You could. If you set certain modes to 0, you could cook something up that has no resonances. But
it would be unlikely.
Yeah, it would be unlikely. And then, if you run your simulation for long enough, what's probably going to happen is that round-off errors are going to cause one of your wave modes that should be 0 to be not 0. And then all of a sudden it's going to start resonating with something. And so because it's a big chaotic system, if you wait long enough, you're going to eventually start to see these resonances.
I see. And what will that look like in a simulation? Is that going to be just like a periodic traveling wave whose amplitude grows, or?
No, it actually, it just looks like noise, basically.
Okay, it looks like this sort of chaotic.
Yeah, so people do this. The original theory was done for water waves, surface water waves, and it actually works quite well in that case. And it predicts, like, the wind will actually put energy into water waves, but only at small scales, only at the scales where capillary forces are important, which is a few centimeters. And it's actually through nonlinear interactions of the waves that energy on small scales goes up to bigger waves. And if you just look at waves on a still pond, you see that there's a wide range of different scales, length scales, and oscillation periods in the waves. And that's actually an example of what wave turbulence looks like. It's not like a soliton moving or something like that. It's just sort of randomish waves.
I see. So the idea is you have a bunch of these modes that are resonating and interacting in a way where you can't visually pull them apart, I guess.
Right. Yeah. The whole point is that there should be lots and lots and lots of these things interacting, because otherwise the theory doesn't. Otherwise, you're back to just like a very large dimensional system of ODEs that's very hard to analyze. But doing the PDE version on the full real line allows you to actually derive these kinetic equations.
And are you kind of making this assumption that high dimensional chaos is behaving like noise? Is that
yes, I mean, to some extent, and people have tried to look at the extent to which that's accurate in various systems, and it doesn't work in every system, especially in certain systems that have coherent structure dynamics, where things are not just really a bunch of random waves interacting. Then wave turbulence can start to break down, and people have tried to come up with theories to try and fix it. In that case, it gets quite complicated.
Yeah. Cool. Other questions for Ian?
Let me do a quick, just before we go, quick advertisement here.
Sure.
So I have a student, Mina Yang, who's graduating. And our second to last project with her was wave turbulence. But we weren't doing the theory, we were doing numerics for wave turbulence and time integration methods. And so we actually looked at like implicit, explicit integrators and exponential integrators and a wide bunch of integrators, and looked at the slow, basically when you discretize a wave turbulence problem with these integrators, and then you do the multiple timescale analysis for the discrete problem, do you end up getting the same result as you get for the continuous problem? And showed that a certain class of methods works and all the other methods don't. And then we ran simulations of a big wave turbulence PDE, and it was quite striking. The methods that work will get you the right answer for a time step size that's 6 orders of magnitude bigger than the other methods. You know, to get the right answer with the other methods, you literally have to do 1,000,000 times more work. But she's graduating in May, so no one is working on that right now.
Cool. Yeah, so that's a nice interaction of the asymptotic theory and numerical methods development.
Yeah, and it was fun to do the 2-time analysis for a discrete problem instead of a continuous problem, which is just a little bit, different than what you're used to seeing.
Yeah.
All right, I won't say anything more.
Thanks, yeah. Anyone else? All right. Would you mind sharing your slides? I'll just put those in Canvas just so people have those to peruse if they like to.
Sure. Yeah, I'll mail them to you.
But yeah, thanks for a nice guest lecture, Ian. Thanks for coming by. And yeah, I guess if people have questions, can they email you?
Sure.
Okay. All right. Cool.
All right. Thanks.
All right. Well, that's it for today. Thanks, Ian, and
Thank you.
see everybody on Wednesday. All right. Bye.